Hello everyone and welcome back to my channel. In this video, I'm gonna introduce you to my new integral formula. Yes, you heard that right. A completely new integral discovered and formulated by me. At first, you might be thinking, that's impossible. It's such a thing excited. Why hasn't anyone else found it? Yeah, that's exactly the point. Because I'm not anyone else. So, what makes this integral different from all the others, and how can it be proven? I designed this formula to describe the fundamental limits of nature, what I call the law of natural boundaries. In reality, everything has a limit. For instance, take Hooke's law, which states that f equals negative key x. Mathematically, the extension seems infinite, but in the real world, it is not physically possible. Likewise, in relativistic physics, we often deal with Lagrangian and four-dimensional system, but how can we express this with a single infinite integral? That's exactly what my formula does. Since the universe operates with four dimensions and follows second-order dynamics with an ultimate limit point, we can represent it through the Philomene integral form like fx equals 1 over the square root of 1 minus x key square over xm squared. It's the max point. That's the point what I choose. And sigma equals 1 infinity fxe and delta x. Now let's take a cluster. Look at this graph and see how it behaves. This form, or make this, and this is the x max, x key is this 0 small equals is less than equal, x key is less than x max point, and look like this, yeah. Or we can write this integral of x equals 1 over the square root of 1 minus x key to the power x key square over xm square integral from 0 to x key of x dx. Or we can write the letter f, and it's looking great. It looks great. And then fx. Now let's assign a special symbol to this integral when it truly represents a sense. But here a question: what happens if we break this integral part? Fx equals integral. There's a new integral form. Fx dx and equals 1 over the square root of, this is 0 x key 1 minus x key square xm square, an integral from 0 x key fx dx. This is the new integral form. And take this. Let's assume that the new integral has two boundaries point, x0 and x. If we product them from 0 to x0 and x to x and 0 to x, and then transform the entire expression into its classical integral form, and the final result becomes the following: fx, assume that negative or non-negative x0, this is the new form, x fx dx, and this is integral this form from 0 to x fx dx, minus integral from 0 x0, fx dx, my integral, this is my integral, that form, and this form, and transform the entire expression into its classical integral form. like this. 1 over the square root of 1 minus x square x mu square integral from 0 to x of x. The x minus 1 over the square root of 1 minus x 0 square over x square max integral from 0 to x0 of x dx. That's true. It's looking majestic. And the next step is, first of all, and this is that the exponential under the radical corresponds after the dimension of the coefficient of the differential we choose. If we take the second integral, this radical term can actually be absorbed into the integral itself, resulting once again in a new radical expression, but now link it to a higher order function. So let's apply this to a real case, the relativistic momentum. Yeah, relativistic momentum. How could we write? And integral, there's a new integral form from 0 to v m dv equals the classical form in classical form 1 minus v square over c square. See the velocity of light, from 0 to v m dv, and this must be equal to mv over the square root of 1 minus v square over c square. Yeah, if we look closely at the result, we can clearly see that it indeed gives us the relativistic momentum. Now, what if we apply the same method to find the relativistic energy? Just as before, we take the integral with respect to velocity and observe how the expression naturally evolves into the energy form. Let's take one integral more. Integral 0 over 0 onto v p. This is impulse the v, and it goes 1 over the square root of 1 minus v square over c square integral the square root of 1 minus v square c square and v from 0 to v, and solve this integral mc square over the square root of 1 minus v square c square integral from 0 to v. And now d1 minus, if we take negative y square and 2 this form, and the square root of 1 minus v square over c square, and we can write 1 minus v square over c square equals t square, and if we take 0, it must be equal 1 equals t square, 1 equals t. Take v, 1 minus v square over c square, the square root of equals t. Okay, and integral negative 2 the square root of 1 minus v square over c square mc square, and integral 0 1 the square root of 1 minus v square over c square, and this is t 2 times t times dt over, this is where, and this is t, and negative mc square 2 times the square root of 1 minus v square c square, and this is and 2, and this is the square root of 1 minus the square root of 1 minus v square over c square minus 1, and this form equals, this is equal m c square over the square root of 1 minus v square over c square. This is 1 minus the square root of 1 minus v squared over c squared. Okay, this is the kinetic energy form. This is a relativistic kinetic energy form. Yeah, you know, mc squared is square root of 1 minus v squared over c squared minus mc squared. And that's right, that's true, that's true. And just yeah, this law doesn't apply only here. It extends to all finished system in the universe. Through this integral, the theory of nature is reflected beautifully and precisely, so much so that it can replace nearly 100 pages of classical physics. If you'd like, it can provide more specific explanation and derivation in future videos. That's all for today. Thank you for watching, and bye.